Okay, we're ready to look at the next thing that we can do with the ideal gas law, and that is to do calculations of density of a gas and molar mass of a gas. So we're going to look at how to do that. Now there's really nothing new we have to learn because we know units for density, we know units for molar mass, but let us just look at the formulas to determine density and the formula to determine molar mass, just to review that for us, okay? So we learned way back in chapter 1 that density is mass over volume, okay? So if I knew the mass of the gas and I knew the volume of the gas, I would just divide those two and I would be able to determine the density of that gas. What about molar mass? Now I'm going to use a script M to represent my molar mass, and my molar mass is grams per mole, okay? So the gram amount, which again is the mass, and the moles of the gas. So that is our formulas for density and molar mass. Now what we can do with this calculation is we can use PV equals nRT to solve for volume, or we could use PV equals nRT to solve for mole, because remember, mole is abbreviated with an N. So let's work through this. Here is our first problem. Calculate the density of the gas in grams per liter, and they give you the molar mass, and they give you the pressure and the temperature, okay? So we're going to determine the density. So we're going to use this formula right here, okay? Now let's look at what they give me. They give me the molar mass, so let's think about how we could use that 54.5 grams per mole. What we can do is decide on what size sample we're having, because the density of a gas is the same whether it's a big sample or a little sample. So I'm going to decide to choose that I have a mole sample of 1, okay? Because if I had a mole of 1, I would then know that the mass is equal to 54.5 grams. So I have a 1 mole sample of gas and it would have this much mass to it. That's important because that will give me the top number of my density. Okay? Now what else did they give me? They gave me a pressure, and that was 1 atmosphere. And they gave me a temperature, and that was 27.0 degrees Celsius. If I take that and add the 273.15, I can get the temperature in Kelvin, which is what I'm definitely going to need in order to use the ideal gas equation. So the value for this would be 300.15 Kelvin. Now I'm ready to work on getting this bottom part of the density. I need the volume. I already knew the mass. Boom, that's this number. Now I need the volume. So we use PV equals nRT. Solving for volume, it is an nRT over P, and I know all of those pieces. So the volume is equal to the number of moles, which is 1, R, which is 0.08206 liter atmospheres per mole Kelvin. As soon as I see that Kelvin, if I hadn't remembered to convert it to Kelvin, I remember now, but that's 300.15 Kelvin. And we will divide by the pressure, and the pressure was given to me as 1 atmosphere. So now what does the volume equal? I do all the calculations for that volume and I get 24.6 liters. Let's make sure it's liters. The moles cancel, the Kelvin cancels, the atmospheres cancels, and I'm left with the liters. So that's the volume, and now I have the bottom number. So at this point I'm ready to calculate the density. Density is the mass, which is 54.5 grams, divided by the volume, which is 24.6 liters. And this will give me a density equal to 2.21 grams per liter. Now, a little mention about the units here. This is a very common unit for density of a gas. We usually use for liquids and solids grams per milliliter or grams per cubic centimeter. But gases are so light, okay, in terms of there's not much mass per volume. And very often we determine the density in terms of how many grams are in a whole liter of them. Okay, so this is how, notice we're not doing anything new. We're using PV equals nRT. We've already learned a while back how to use density. We're using these things that we know and we're combining them together to determine the density of a gas. Okay, we're ready to do another problem similar to our last one, but in this one we're going to calculate the molar mass of a gas. Now we remember that molar mass is the grams of the gas per mole of the gas. Those are the units that we need to have for that. And we look through this problem, and in this problem they gave me a density. The density of the gas is 1.14 gram per liter. So once again, what we'll do is decide the sample size, because it doesn't matter whether it's a big sample or a little sample. The molar mass of the gas is not dependent upon how big our sample size is. It's just a matter of determining how many grams are in each mole. So what I want to choose is a 1 liter sample size. So my volume is going to be 1 liter, because if my volume is 1 liter, I then will know that the mass of this gas is 1.14 grams, because I know there's 1.14 grams in every liter. As soon as I know the mass, I know the top part of this molar mass. I've got that settled. And all I need to know is the moles. Well, since it's a gas, we know that PV equals nRT, and we can solve for N. So N is equal to PV over RT. Let's see if we have all those things. We certainly see the volume here, and we always know R, but did they give me pressure and temperature? Well, as I look there, it tells me that the pressure was 1 atmosphere. So I have the pressure, and the temperature is 27 degrees Celsius, and in the previous problem we saw that 27 degrees Celsius is 300.15 Kelvin if I have extra sig figs past the decimal point. So now I have all of those pieces there, and I can solve for the number of moles. So the number of moles is going to be the pressure of 1 atmosphere, the volume of 1 liter, because I chose a 1 liter sample size, a R of 0.08206 liter atmospheres per mole Kelvin, and a temperature of 300.15 Kelvin. So there's all the parts that I needed in order to determine the moles, and that gives me 0.0406 moles of this gas. So at this point, I now know the bottom part of my molar mass, and I can determine the molar mass is equal to the grams, which I said was 1.14 grams, divided by the moles, which we just calculated here, 0.0406 moles. And when I divide that out, I will get a molar mass of 28.1 grams per mole. Okay, so that is a reasonable molar mass. When I see that number, having a gas with a greater than 2, because that's H2, that would be the smallest thing that we could have that's a gas. It's not huge, and things that are gases typically have, molar masses around that value looks good. All right, so that is how to calculate using the calculate the molar mass. Again, I want to emphasize that we didn't have to learn anything new in order to do these problems. We use an equation that we already knew, we have molar mass that we already know about, and we're just combining them together in order to get the molar mass of a gas. Now, if you know the identity of a gas, you can always go to the periodic table and you can calculate the molar mass. But this is a way to obtain a molar mass when you don't know what the identity is, but you just need to know, okay, how much did it weigh in grams, what's the moles, and if you had some source of getting that information, you would be able to get the molar mass of this unknown gas. Now, I want to put this formula up for you. The book provides this formula, and I do not have it memorized, okay, because there was nothing here that I didn't already know how to do. And this might save me a little time, but to me it wasn't worth memorizing. Let's see what we have here. This is a way of relating density to molar mass. So we know that D stands for density. This is my symbol. It looked like a script M on a different font computer, but that's my molar mass. Okay, so we see the pressure, the R, the T being given to me, and it's kind of doing what I'm doing in one equation. Many students love to memorize. I wouldn't say that. They don't love to memorize things. They feel comfortable memorizing things and using equations rather than putting it together. I would much rather see you understand what I did, because you don't have to memorize a little bitty fact, than just taking this equation and applying it. But it's up to you. You choose what method you want. This would just be another way of getting between density and molar mass from a given equation. All right, so I want you to try one. What you're going to do here is you are going to stop the video as soon as I'm done talking. Stop the video and work through this problem and select one of those answers. Once you have one of those answers, resume the video and we'll give a check to see how you did. All right, hopefully you took the time to do that and picked an answer here. Now this is the correct answer, C. It's 2.90 grams per liter. Now if you got that answer, you're in great shape and you're done with this lesson if you feel very comfortable in it. If you picked A, what's likely to have happened is you forgot to do the conversion that we did here to Kelvin. It's 25 degrees Celsius. That would have been 298 Kelvin. You should have been using that for this problem. If you picked B, you were almost there. It said chlorine gas, and I keep on trying to catch you with this. Chlorine gas, if you think about the Hofbrinkels, that is one of the diatomic molecules, and you needed to use the molar mass of chlorine and not the molar of Cl2, not just Cl, to get that problem. And D is if you did both. You forgot to convert to this and you forgot to that chlorine is Cl2, then you might have picked D. So if you look down at your work and you say, oh yes, I forgot to convert to Kelvin, or oh, I didn't even think about chlorine being Cl2, you've figured out your mistake, you won't make that mistake again, and now you're done with this lesson. But if you still feel a little bit shaky on how to do these calculations, I'm going to go ahead and work through this problem in its entirety for you, and you can watch how I work it. Okay, so I'm going to kneel down here and work through this problem for us. So it says here I'm trying to calculate the density. So, and I can actually move over a little bit. Density equals mass, or grams, over volume, which is in liters for this case. I have a chlorine gas. So Cl2 gas has a molar mass of, well, it's 2 times 35.45 grams per mole. So that would be 70.9 grams per mole. So what I could choose is a 1 mole sample of gas, okay? So my N is 1 mole, okay? And if my N is 1 mole, then my mass has to be 70.9 grams. So now I know the top part of this equation. To get the bottom part of this equation, I'm going to use PV equals nRT and solve for V. So V equals nRT over P. And I start looking for all of that information. N is 1. We know R, 0.08206. See that Kelvin there? It reminds me I need my temperature in Kelvin. 25.0 degrees is 298. Go ahead and carry extra sig figs. That's in Kelvin. And divide by the pressure. They tell me it's at 1 atmosphere. So now I've got all that I need in there, and that's going to give me the volume equal to, let's see if I can fit it on here and you all can see it. No, you can't see it there, so let me put it over here. Volume is equal to, in this case, 24.5 liters, and now I have the bottom part of this equation, so I'm able to determine the density by plugging that information in. The mass is 70.9 grams. The volume is 24 2.5 liters, and that is going to provide me with a density equal to the answer that we see there of 2.90. And that's grams per liter. And you can't see that, so I'm going to move it up. Sorry about that. This is equal to 2.90 grams per liter. Okay, so that is the conclusion of how to use molar mass to get to density, or use density to get to molar mass.